Hello, my name is Vladimir Korikov, and this is the Domain-Driven Design in Practice course, starting with the first bounded context. In this module, we will begin the actual development process. We'll start off with the basic functionality for our model of a snack machine, inserting coins and notes to the machine and returning the money. You will see how entities differ from value objects and learn the best practices for working with them. Before we start, let's take a minute to define the terms we'll be using in this course. You might have seen many of them in the past, but it's not always clear what they mean in different circumstances. First of all, I use the terms problem domain and domain interchangeably. They mean the actual problem our software is going to solve, the purpose it is built for. The term core domain is a subset of these two. It is the essential part of the problem domain, the part which cannot be delegated to an external solution and must be resolved by us developers. Also, the terms business logic, business rules, domain logic, domain knowledge, and domain model are synonymous. You can think of them this way. The business logic you enclose in your code represents the knowledge that you as a software developer have about the problem domain. You express this knowledge by codifying a model of the domain you are working in, hence the term domain model. The business logic of an application typically resides in the two innermost layers of the Angular architecture. I refer to the notions from these two layers as domain classes. So a domain class might be a repository, an entity, and so on, but not an application service. We will talk about the application services in the next module. The first bounded context we will start with is snack machine. We will talk about the ways to represent bounded context later in this course. For now, we will focus on the machine model implementation. Our first task will be to model the way it works with coins and notes. So what are the operations we should be able to perform with money? Obviously, we need a way to insert them into the machine. Also, if we change our mind, then we should be able to take the inserted money back. And finally, we may want to buy something. In this case, the amount of money we inserted should go to the machine permanently, and we should get back the change. We will take a shortcut in this module and implement a simplified version of the purchase functionality. We will extend it in the future modules. We'll start the development with the core domain, the model of the snack machine. Here's the solution for our application. I named it DDD in practice. You can see there is only one project currently, named Logic. In it, we will store our business logic, utilities, and data access code. This is the class for the snack machine. Note the use of the sealed keyword. It's a good practice to give your code as few privileges as possible by default. So, to insert money to the snack machine, we need to have a place where the coins and notes will be stored. The easiest way to do this is to introduce separate properties for each type of coin and note, so that we know exactly how many of them are in the machine right now. You can see here a separate property for the number of 1-cent coins, quarters, and so on. The actual method then could look like this. We accept any amount of money and just add them to the money we have in the machine. So far so good. The second function our snack machine should have is the ability to return the money we inserted in case the user changed their mind. This raises a problem as we don't distinguish the money the user inserted from the money that was in the machine beforehand, so we can't say how much money we should return to the user. The solution here is to introduce a separate set of properties which would define the amount of money that is currently in a transaction. This is the money the user will be able to get back or use to make a purchase. When the user inserts a coin or a note, this money is added to the money in transaction instead of the money that belongs to the machine, so we need to change the insert money method, like this. The return method then just returns all the money that the user inserted. We can model this behavior by nullifying the corresponding properties. And finally, we should be able to buy a snack. For now, we can depict it like this. Just move all the money in transaction to the money inside the machine and nullify the transaction money after that. Alright, let's overlook this implementation again. There is a concept here which can be extracted out of the snack machine class. I bet you already guessed that it's the notion of money. Indeed, we have two identical sets of properties. They represent the money the machine has, the amount of money inside, and the amount of money inserted by a user. We can introduce an abstraction, a new class called money. And now we are able to move all the money-related members to this class and also add an addition operator to it. What this operator does is it introduces a plus function. It takes two money instances and creates a new one which consists of all coins and notes from the original two. Now we are able to add just a single property, money inside, and remove all these properties from here, and another one for the money in transaction. The insert money method can also accept a money instance instead of the separate count parameters. Here we make use of the plus operator we introduced in the money class. For the return money method, we will also need to introduce some operation for clearing up the money instance to show that there is no longer any money in the transaction. We will talk about it later. For now, I'll just comment this line out. For the buy snack method, we are moving all the money in transaction to the money inside and also nullifying the instance. You can see here, after we brought a new concept, money, the code of the snack machine became much simpler. This is no coincidence. You will see that introducing a new abstraction often makes the overall solution easier to understand and maintain. Let's recap what we came through in the previous demo. First of all, you saw we started with the core domain right away, without modeling the UI or the database first. It's a good idea to always do this. You should always begin the project by experimenting with your domain model, as it's the most important part of your application. Secondly, always start with a single bounded context for all business logic in your application. Don't try to divide it into several pieces upfront. While bounded contexts help reduce complexity of your code, the application is justified only when your code base is quite big already. Otherwise, they won't reduce the complexity, but rather increase it instead. And thirdly, constantly evaluate your code and look for hidden abstractions. You saw that after we introduced the money class, the code of the snack machine was simplified greatly. In our case, the presence of this abstraction was pretty obvious, of course, and it's not always possible to identify one in a more sophisticated situation. Nevertheless, if you see your code becomes awkward, you should test different approaches and examine if they fit your problem domain. It might be there is a hidden abstraction in your domain model that you didn't express just yet. At this point, we approached an important topic, the difference between entities and value objects. In our codebase, we currently have two classes, snack machine and money. They seem pretty similar to each other, but their semantics differs significantly. The snack machine class here is an entity, whereas money is a value object. Let's elaborate on that. The main difference between entities and value objects is in the way we identify them. There are three types of equality when it comes to comparing objects with each other: reference equality, identifier equality, and structural equality. Reference equality means that two objects are deemed to be equal if they reference the same address in the memory. Identifier equality implies a class has an ID field. Two instances of such a class would be equal if they have the same identifiers. And finally, with structural equality, we consider two objects equal if all of their members match. So how does the way we identify entities and value objects differ? The difference here is that identifier equality refers to entities exclusively, whereas value objects possess structural equality. In practice, it means that value objects don't have an identifier field, and if two value objects have the same set of attributes, we can treat them interchangeably. It makes a lot of sense if you look at the notion of money in our domain model. If we have two $1 bills, it doesn't really matter which of them we work with. We don't care about their identity. We can easily replace one set of coins and notes with another one, as long as these two sets have the same composition. At the same time, even if two snack machines have the same amount of money inside, we don't treat them interchangeably. We do care about which of them we work with. You can think of it in a similar way you would think of two people bearing the same name. We don't treat them as the same person because of that. They have their own inherent identity. Another distinction between the two notions is immutability. Value objects should be immutable in the sense that if we need to change such an object, we construct a new instance based on the existing object rather than changing it. On the contrary, entities are almost always mutable. The next difference is that value objects cannot live by their own. They should always belong to one or several entities. In our application, money doesn't make sense without a snack machine. If it does, the money class would be an entity itself. We can put it another way. There always should be at least one entity that owns a value object. Again, in our case, it is the snack machine class, which contains two properties of the money type. An important implication from this point is that value objects don't have their own tables in the database. We will talk about it in more detail in the next module when we'll be discussing persistence for our domain model.